Let me go back here. Okay, so once again, this section 2.3 provides a review of most of the concepts introduced in the first chapter in relations to systems of n linear equations and n unknowns and to square matrices. The main result is Theorem 8, which is called the invertible matrix theorem. Okay, let me bring this theorem up for you. Ta-da! There it is. How many of you is this like maybe the biggest theorem you've seen in your life? The invertible matrix theorem. Okay. Okay, Eleanor's wow, Olivia's probably. Well, you'll be happy to know. Yeah, well, I agree, Ariana, but a lot of these concepts are very intuitive based on your learning you've done already. So, of course, the invertible matrix theorem only applies to square matrices. And it says the following statements are equivalent. That is, for a given matrix A, the statements are either all true or all false. Okay. So, like for instance, if A is an invertible matrix, okay, then this implies that AX equals 0 has only the trivial solution. Okay, let's talk about that. You know, why does statement A imply statement D, and statement D implies statement A? So why is that true? Why is that true? Let me go to the so you have your ebooks there, but let me go to the whiteboard for a moment. Okay, and let me see here if I can. Whoops, hold on. Thank you. Thank you. Sorry, I was too focused on my thing. Hold on here. Thank you, Nafani. So let me go back here. So what we're doing is we have a statement. So I'm thinking about the invertible matrix theorem. I'm thinking about why does statement A imply statement D? So statement A is that A inverse exists. Apparently, if the inverse of A exists, this implies that the matrix equation AX equals 0 has only the trivial solution. So again, from the invertible matrix theorem, that's theorem 8 in section 2.3, we're implying statement A implies statement D. So I want to prove this. I want to show this. Okay, and so what I do is I write down the equation A times X equals 0. I write that down. And then what I want to do is I want to multiply on the left side, I want to multiply the A times X vector, that's a vector, by a matrix, by something here on the left. Okay, and then I want to multiply the 0 vector by something on the right side of the equals. So what I'm asking is, what should go here? What can go there? What would make sense to put there? Well, what do we know? The hypothesis is that A inverse exists. So what can we put here on the left? What can we put right here? What can we type in there? Ah, good, Haley. A inverse. Good, Nafani. All right, so I'll do that. I'll put A inverse here. I'll multiply by A inverse there on the left, and I'll multiply on the right side of my equation by A inverse on the left. Okay, well, what is A inverse times A? Good, that's the identity. Good. So I'm going to get the identity times the vector x equals A inverse times the 0 vector. What do you think A inverse times the 0 vector is going to equal? That's right. Good, Benjamin. Good, Nafani. A inverse times the 0 vector is just going to equal the 0 vector. Okay, and therefore, and I times x is just going to be, well, what is the identity times the vector x equal to? The vector x. Good. So you end up getting then that the solution vector x is equal to the 0 vector. Hey, that's the trivial solution. So you've proven part of the invertible matrix theorem. Theorem 8 from section 2.3. That wasn't too hard, was it? Are there any questions on that? All right, well then let me go back to the theorem, okay? Let me go back to the theorem. Okay, so there's a really, this is going to be a very useful theorem. You're going to be using it a lot this semester. So I mean, here's another thing. If A is invertible, it turns out um, that the columns of A span n-dimensional space. A implies H, and H implies A. If, for instance, A is an invertible matrix, the columns of A have to form a linearly independent set. Okay, so there's a lot of a lot of implications here when we have an invertible square matrix. A lot of nice things happen. So what I'd like to do is I'd like to prove just a few more of these statements because I think it's useful, and then we'll see where we go from there. But are there any questions on this? Okay, maybe actually I'll bring up example one. Hold on, hold on. One moment, class. Okay, so like I was saying, the invertible matrix theorem, like if A is an invertible matrix, that's statement A, that's going to imply statement E, that the columns of A form a linearly independent set. Okay, that's a pretty powerful statement there. Also, if the columns of A form a linearly independent set, that means then that the columns of A have to span n-dimensional space. Okay. Or if the columns of A span n-dimensional space, the linear transformation, or the matrix transformation, multiply A by the vector X, that's going to be a one-to-one transformation. Okay, so I think some of these are intuitive, but let's go ahead and look at a few examples. Can everybody see the book okay in the window here in Blackboard? Yeah, I'm seeing that too. I don't know what's going on. Hold on. Let me go back here. Hold on, class. One moment. I'm gonna have to reopen this thing. Hold on. Just give me a moment here. Okay, chat it out to me if, I mean, you can see it now okay? The theorem, wonderful, thank you. So the point is that if A is an invertible matrix, it implies a lot of things. For instance, the columns of A if A is invertible, the columns of A form a linearly independent set. Statement A implies statement E. Statement E implies statement H. If the columns of A form a linearly independent set, then the columns of A span R of N. They span n-dimensional space. Okay. If the columns of A, statement E form a linearly independent set, that implies statement F, that the linear transformation, taking A and multiplying it by the vector X, it's a one-to-one transformation. So there's a lot of cool things. And what you can do is you can use, they give kind of a big proof of this theorem, but let's just not, I mean, we're going to look at a few aspects of that theorem. We'll try to prove a few things. But here's another fact that's important. If you have square matrices A times B, and A times B equals the identity, okay, then A and B are invertible, and B will equal A inverse, and A will equal B inverse. You're going to prove that actually in your homework. You'll prove that statement in your homework for section 2.3. All right, let's continue on here. So, okay. Let's see here. So, if you have an invertible matrix, well, use the invertible matrix theorem to decide if A is invertible. Here's a matrix A. Okay, so the idea here is, you know, let's just use the invertible matrix theorem to help us. So what they do is they do some row operations, and they get the matrix A into what form is that? On the right, is that echelon form or reduced echelon form? On the right. What do you think? Okay, so I like it when I get, you know, I like everybody participating. It would actually be echelon form, because the last column, there's a pivot in the last column, that 3, and for reduced echelon form, what would that pivot have to equal? In the third column, it'd have to equal 1, good, and then the numbers above that pivot would have to be 0. So, but the point is, you do a few row operations. So obviously, what they did on the first stage here is they took the they took the first row, multiplied it by -3, added that to the second row, put the result in the second row, and then they took the first row, multiplied that by 5, and added 5 times the first row to the third row, and put the result in the third row. And then going from this matrix to this matrix, okay, the row equivalent matrix, they took the second row, added it to, you know, 1 times the second row plus the third row, and then put the result in the third row. And that's how they got to the echelon form that you see here. Okay, that's how they got to the echelon form. But now A has 3 pivot positions, and therefore it's invertible by the invertible matrix theorem. Okay. So the invertible matrix theorem, well, let's see. If we go up here to the invertible matrix theorem, okay, let me just remove these yellow highlights. I don't know why that showed again. I took it off. Hold on, class. So well, I'm sorry, I don't know what's going on here, but we showed that part C that A has n pivot positions. We have 3 pivot positions for that 3 by 3 matrix, and therefore A is then that implies statement A, that A is an invertible matrix. So here statement C, because statement C implies statement A, the fact that our 3 by 3 matrix A had 3 pivot positions, that implies that the matrix A is invertible. Okay, so that's an application. Example 1 in the book here is an application of the invertible matrix theorem. And in your homework for section 2.3, there's a few free response questions, a small assignment for I think 3 questions from section 2.3 that are free response, but then a lot of questions from section 2.3 that are multiple choice. And it's to assess your understanding really of the invertible matrix theorem. Okay, and all right. So that being said, let's go ahead and let's look at a few more examples here, because I think if you understand a few more, if you can appreciate a few more statements. Hold on here. If you can appreciate a few more statements that why they're true in the invertible matrix theorem, I think you'll appreciate the invertible matrix theorem. So let's go ahead and in this example, we're assuming we have a square matrix naturally, and we want to show that if the matrix A is invertible, okay, then the columns of that matrix A span Rn, n-dimensional space. So what we're doing here is we're saying, you know, this is statement A. A is invertible, and then the columns of A span Rn is statement H. So what we're doing here is we're trying to show why statement A from the invertible matrix theorem implies statement H. Okay, let me give you a moment to catch up here. Okay, so let's prove this statement here. Are we ready to move to the next page? Okay, thank you, Nafani. Okay, Ariana, very good. All right. Let's prove this statement. So let me ask you, when we prove this statement, what's the only thing we know about matrix A? When we try to prove this statement, we need to start off. We need a starting point. What do we know about matrix A? That it has an inverse. That's right. Good and funny. All right, well then let's go to the next page here and look at the solution. Okay, one moment here. Yeah, this is good. So what I do is I write the matrix, the n by n matrix A, as a matrix with column vectors specified, A1, A2, up to AN. I mean, certainly that's true. We can write a matrix A in terms of its column vectors. We can represent it that. We can represent it this way here. And if the matrix A is invertible, then certainly for every vector B in n-dimensional space, AX equals B would have to have this solution. Okay. And that's true. Well, let me, we'll talk about the reason why that's true. Let me give you a moment to catch up. I want to make sure I'm not going, I want to pace myself properly here. Okay, so, why does, well, X equals A inverse times B, that's going to be true. If we consider the matrix equation A times X equals B, it will have this solution X equals A inverse times B. And that's true simply because I show it all along here. Okay, and I think, have covered this before. I mean, this is the justification why. Are there any questions on this justification here? All right, but the key is that the key statement here is that the matrix equation AX equals B has a solution vector X. The solution vector X is described by A inverse times B, but the point is there is a solution. There must be a solution to this matrix equation here. Okay, may I go to the next page? We still, I mean, this is nice, but we still, we still have to be able to prove then that the columns of the matrix A, these columns here, okay, these columns here, the columns of the matrix A span n-dimensional space. We're not there yet. But let's go to the next page. All right, so if the matrix equation AX equals B has a solution X for every B in n-dimensional space, then equivalently, this statement here is true. This statement here. What is that statement called? That's a special equation. We give a name for this equation. What kind of equation is this? I'll give you a hint. Begins with, oh wow, Benjamin beat me to it and Hung beat me to it. And Olivia beat me to it. It's a vector equation. That's right. That's what it is. It's a vector equation. And does the left side of this vector equation equal the matrix A times the vector X? It does. Absolutely. And you've learned this. You've learned how to write a matrix equation as a vector equation. And the fact that the matrix equation and hence the vector equation, the fact that by virtue of the fact that A is invertible, this vector equation has a solution, vector X, for every vector B in Rn space. And that means for any vector B in n-dimensional space, that vector B has to be in the span of the column vectors of the matrix A. Because on the left here, on the left, I mean, what you're saying here in this statement is that vector equation, if it holds true, and it does, it means that the vector B can be written as a linear combination of the column vectors of the matrix A. And that means that B is in the span of the column vectors of the matrix A. And therefore, the column vector, the columns of A span Rn. And we've just proven the statement. How many think that's pretty cool? This might be the first time you've been exposed to sort of theoretical proofs. They're not like super long. Thank you, Benjamin. They're not, I mean, linear algebra is usually the first course in which students are presented with proof type problems. They're not like long proofs, but I hope more than Benjamin likes this. Are there any other people that think, hey, this is kind of neat? Okay, Lewis thinks it's cool. Olivia, okay, great. Well, do you want to do another one? Justin, I appreciate that. I like proofs. They're helpful in that you appreciate the theorem. This invertible matrix theorem, we want to feel good about it. So. All right, you want to try another one? That's right, Shravani. They do help navigate what you're finding. Absolutely. All right, are there any questions before we move on? Okay. All right, everybody's done copying, okay? Okay, thank you, Shravani. All right, well, let's move on then. Let's move on. Let's look at another, let's prove another part of the invertible matrix theorem. So here we have a square matrix, and we want to show if A is invertible, then the columns of A form a linearly independent set. Okay, so in other words, in the invertible matrix theorem, we're showing that statement A implies statement E. That's what we're proving here. Okay, so let's see here. All right. Well, there is a matrix equation that I want to exploit in this proof. Well, I want to be a little bit careful. Let's just go to the proof here. Let's just go to the proof. So, okay, so again here, we write the matrix, we represent the matrix A as the matrix of its column vectors, its columns. And if it's invertible, then the matrix equation AX equals B has the solution X equals A inverse times B. But now here's what we do. We say, okay, let's let the vector B, let's just pick the vector B as the zero vector. I mean, for any vector B, AX equals B, that matrix equation will have the solution X equals A inverse times B. It's true for any vector B in n-dimensional space. Well, the zero vector is a vector in n-dimensional space. So this would mean then that AX equals 0 would have to have the solution X equals A inverse times B, but B is 0, so X equals A inverse times 0, which is the zero vector. Okay, so therefore, well, let me give you a moment to catch up to here. I know you're copying down notes, so I like to take my time. Okay, so now the, I want to be careful here. No, yeah, this is fine. Again, here, well, what does the left side of this equation equal? You have a vector equation here, and on the left-hand side, you have a linear combination of the columns of the matrix A. But what does the left-hand side equal? It's the product of, okay, good. That's what I'm looking for, Nafani. I was going to give you a hint, but Nafani got it there. Yeah, that equals A times X. So we know that A times X equals a zero vector can be written as this vector equation. Why do we want to do that? Why do we want to do that? Well, we know that we want to get to linear independence of the columns of A. The columns of A form a linearly independent set. So the fact that A times X equals 0 means that the linear combination of the columns of the matrix A would only have the solution X equals 0. So all these weights here, x1, x2 up to xn, all of those weight values will equal 0, which is the trivial solution. Hence, the columns of A form a linearly independent set. I mean, that's the definition of linear independence. If you have a vector equation, just like this here, you have this vector equation, and the only solutions, the only values that would be true would be all the x variables equal 0, then the vectors x1, the vectors a1, a2 up to an form a linearly independent set, and so the columns of A form a linearly independent set. And you've proven another piece of the theorem. It's really quite beautiful. Are there any questions? Okay, how many of you like these little proofs? If you do, there's a course called topology that you can take when you'll probably, it's offered like at four-year universities, but that class is basically, okay, Eleanor likes that, the proof's wonderful. That class, I took that, and topology, and basically the course is proofs. So, the exams, I remember the exams I took were all proof problems. But but it really, it's kind of it's a nice course, Okay, great. Are there any other questions before we move on? All right, very good. Well, so we could, spend some more time look at proving statements in the invertible matrix theorem, but I think right now I'd like to hold off, but I'm going to do one more thing. Let me do one more thing here. Let me do one more thing with you, because I'm thinking about the type of problems you're going to see in section 2.3, and I just want to kind of run something by you here. So let's say, hold on here, let me try to use my little drawing tablet. Okay, let's say you had this 3 by 3 matrix A. And I'm sorry, I'm getting used to this tablet, but I can certainly write faster with the tablet. Okay, so is A invertible? And I don't want you to go into MATLAB and, try to do inverse of A to see if it's invertible. I want you to, just based off of this matrix A, can we say is A invertible? Think about the invertible matrix theorem. I mean, let's say I don't want to type this matrix in MATLAB. I just want to be able to say if it's invertible without, typing it in. Benjamin thinks it's invertible. Nafani thinks it's invertible. Okay. Well, all right. The answer is yes. But why? What reason can you give for this matrix being invertible? Good, Justin. Very good. Very good, Hum. There's a pivot in every row. Every row has a pivot. And by the invertible matrix theorem, if you have, like in this case, you have a 3 by 3 matrix, you have 3 pivot positions, and therefore the matrix is invertible. Okay. Well, that's actually true too, Nafani. Nafani's looking at the columns. That's another way to see it. The 3 columns, hold on, sorry, I got to get used to this. The 3 columns here are definitely linearly independent columns. And so the fact that you have 3 linearly independent, you have a 3 by 3 matrix A, its 3 columns are linearly independent, that also means that the matrix A is invertible. So you see this is the way you want to do the multiple choice problems from section 2.3. That's the way you want to work them. So, okay, all right. Let me stop there. Are there any questions at all? Okay, let me stop the recording.